Okay, thank you.
Greetings and welcome to today's Power Virtual User Group technical webinar. This is Jyoti Dodia and I have Stuart Cunliffe here to talk about OpenShift Container Platform 4.3 on IBM Power Systems. So over to you, Stuart.
Thank you, Jyoti. I'm not sure my time's that valuable at the moment. I seem to spent the last 3 months homeschooling and learning things like fronted adverbials and things like that. But it's nice to be on. Thank you all for joining. I hope everybody's well. Yes, as Jyoti said, my name is Stuart Cunliffe. I work in Systems Lab Services. I'm going to talk to you today about OpenShift Container Platform version 4.x, we're going to call it 4.3 for now, on IBM Power. I ran a session similar to this some time ago now on version 3.11. So I'm going to go through some of the differences. So if we have a look at the agenda, just apologies as well. If it does get too noisy, I'm in my man shed at the top of my garden and there's lots of birds outside in the tree. So if it gets too noisy, please ping Jyoti and she'll interrupt me and tell me to go and close the doors. So this is the agenda that I'm going to run through today. I'm going to run through what is OCP, what is OpenShift Container Platform from a very high level, just to make sure everybody's on the same sheet. Then the differences between version 3.11 and version 4, and there's lots of differences, but I'm going to go through the core differences, especially the ones that affect us within the IBM Power world and the architecture side, I think. Then I'm going to show you a video of the installation of OCP on our user provisioned infrastructure, so our IBM Power VM environment. And this is a video because in my environment it takes about an hour and a quarter, an hour and a half for it to run through, and I didn't really think you'd want to be sitting there watching that video. I'm also going to show you a video of an upgrade process, again shortened down to a few minutes, so as opposed to the usual hour that it takes. Then I'm going to show you around OCP, the GUI and the command line, and then running some workloads on those. This presentation will be available for you to download. Obviously, if you wanted the videos, contact me because I'm going to put them into the bundle because they'll probably be too large. And I'm going to be flicking between quite a lot of screens between my PowerPoint and my Firefox and my command line. So please bear with me if some of the screens fade away for a little bit. So, okay, hopefully that's what you've come to expect. So let's crack on. So first of all,
Stuart, sorry, can I just interrupt? I just wanted to tell people that if they want to ask questions, please do so via the chat window. And also, if you could just type in where you're joining us from today and what your local time is, it just gives us an idea. Thank you so much.
Sure, no worries. Yeah, so obviously I can't see the questions as they come up, but either during or afterwards we'll take some time and try and answer. And if I can't answer them, I'll get back to you and we'll do it over email or Twitter. Okay. So why do we need OCP? The lowest part of this jigsaw is for us to be able to run containers. So our containerized environment is effectively a operating system level virtualization. So on the left-hand side of this picture, we had our traditional deployments where we had a bit of hardware, we stuck an OS on it, and then we ran a few apps on there. Then virtualization from a hypervisor level came along. Here we're showing operating system hypervisor, but obviously on Power got Hyper-V, where we were able to install multiple operating systems and run applications on top of those operating systems. But those applications were full operating systems with the full binaries and libraries associated with that operating system. Then containerization came around where we had a runtime environment, an operating system, which lets us share the Linux kernel amongst various applications. So we have a container, which is a minimal version of the operating system with the binaries and libraries needed just to run the application. And we can fire them up, we can close them down, they can be permanent, they can be transient and what have you. So a lot smaller. So we can package the application with its dependencies just into a container to be able to run should we need to. We have Docker, we have runtime, container runtimes such as Docker or CRIO, and they help us do that work around creation, deployment, and running. And the container image is lightweight, it's standalone, it can be run anywhere effectively as long as that Linux kernel is available. So we can, it's very, very portable. It's very, very fast to start up. We have a number of advantages and disadvantages. Obviously, they're lightweight, they can be isolated, minimum dependencies are very small. We can put lots and lots of containers onto a single VM. We can condense a lot more. We can upgrade just single containers, or if we need to, as opposed to the whole virtual machine. And it allows our developers, which is the key to this, to be able to develop their application, test their application, roll them out across different multiple environments. Some of the disadvantages, it's Linux only. We are sharing an OS kernel. And if you think about it, you've got hundreds, maybe thousands of containers to run, where in the old days, you might just have the application running on 2 or 3 virtual machines. For example, OpenShift on its own, OpenShift version 4 on Power, is a minimum of 200 plus containers running in the background. However, this is where OpenShift comes in and does its business. Where do we get these images from? There's lots of different places. Docker Hub has got most of them. Obviously, private repositories such as Red Hat, I've got them in there. I think the last time I checked, PPC 64 little endian containers on Red Hat was 700 plus, ranging from base OSs up to applications that we might want to run on them. So go onto there, look around, see what there is. You can search on PPC 64 little endian, find out which ones are Power, look at the manifests to see if an image has got availability in AMD and Power maybe, and see what there is that we can download. If we wanted to run a simple container, we can run from my host. This is actually on my Mac. I'm running Docker on my Mac. I run a Podman run. I've got Podman alias to Docker. I can just point it at a CentOS. So I've got a CentOS image somewhere off in Docker Hub, and it goes and runs, logs me on. If I do a grep for the OS, it tells me it's CentOS. To a host name, it's giving it a random host name generated. All well and good. How do we, if we wanted to create our own images? Well, we can deploy a base image, maybe a RHEL 7 or a RHEL 8 one, or CentOS in this case, as I'm showing. We could log onto that container. As I just showed you on the previous screen, we can install RPMs, add users, copy files, scripts, everything like that. And then if we wanted to, we could take a copy of that image, push it back to Docker or repository in Docker, and call on that image further on down the line should we want to use that. Not very agile, not really the best ways to do it. What we tend to do is methods such as building them via Docker file. So what we have here, we have a flat file, which I'll show you an example of in a minute, which takes the base image and then during the build process acts upon that base image to get it the desired configuration that we want. So those steps I mentioned earlier about installing RPMs, adding users, copying files, we place this in the base Docker image. So what comes out at the end of it is one image that contains all the steps that we previously defined. It does layer them up and it does create a little image as it goes along, but at the end we just have the one. We then have the one image that has everything that we require. This is an example of a Docker image. So here we've got an example where we've pulled an image called Ubuntu, so from Ubuntu, we've issued command, we've maintainers, we've done an update of the Ubuntu operating system, we've installed node-red, added users, groups, installed npm node-red, exposed a port, and then started. The last thing we do is start the application. That's fine. We do a docker build dot. So in other words, look in my local directory for a Docker file and then tag it with this image. And then we've got an image and we can push that back up to Docker if we want to, which is all well and good if you're working on your own, you're working on your laptop. What can we do if we want to work on a combined Docker file? So here's an example where my Docker file is on GitHub. So I've put exactly the same file into my GitHub file and I've done a Docker build, pointed to my GitHub repository, and it's gone away and done the build from that. So if somebody made a change, the next time I ran it, it will pick up that change when I did the Docker build. And then when I push it to Docker Hub, there you can see my node-red ISS version 8 and some of the commands down the bottom that I ran within my Docker build. So that's all well and good, but even though containers are the lowest part of the jigsaw that we want to run, what about running them in large development and production environments? We might end up with a huge amount of containers. How do we manage all these? how do we let the Docker, the containers communicate with each other? What should we do if one fails? How do we scale? If we want to add persistent storage, how do we upgrade? All those sort of things is the key to running containers in an enterprise environment. And that is where Kubernetes comes in, or K8. So K8 we can think of as the orchestration layer around all these containers, how it's going to manage the containers across a group of physical servers or VMs in a cluster. And the design around Kubernetes, so Kubernetes was originally designed by Google. It was released to the community, so to the donated to Cloud Native Computing Foundation, CNCF, that's right, about 6 or 7 years ago as a project. And it's available in GitHub as a project, written in Go. You can go and drag down the raw basis of Kubernetes if you want from the project. It basically manages the cluster around these containers. So we can deploy, we can scale up, we can keep control of our cluster, we can add communications, storage, we can monitor them and what to do. We can inform the cluster what to do if a container or a pod fails. I'll talk about differences in a minute. So we have controllers that are constantly looking at our cluster and taking action on this. We can run it on premise, we can run it on the cloud. There's lots of offerings out there, such as IBM Kubernetes services and Azure and Amazon, and obviously there's Red Hat OpenShift as well. So a couple of terminologies before we get going. So a node is a VM or server that runs a workload. That's quite key. I'll talk about 2 different types of nodes in a little bit, or 3 different types of nodes in a bit. A pod is what we call a collection of containers. So a pod is the smallest denominator that OpenShift will refer to. So a pod contains containers. Now, normally a container might just contain one, but we can have other containers which are all related to the same pod within that pod. It can be sidecar containers that help the main container do its work. So if we think of pods at a high level, let's just think of pods as containers. Projects, we have reserved namespaces for projects, so we can isolate workload, and I'll show you adding and using certain projects. Services, where we collect pods together and we expose them as an endpoint, so we have one endpoint into a group of pods from a communication perspective, and then routes, where routes will then expose those services for external communications to our developers or our users. And then deployments, where we create the pod and replica sets in a single configuration, and I'll show you an example of those as well. A quick look at the architecture. So I mentioned nodes. We have the concept of a master nodes or control planes, which run the key services that control the cluster. So the API access to them, the scheduler of where workloads are going to go, the controller manager, which is obviously very key. So it constantly is looking at the pods and the worker nodes to make sure everything is in the correct state. And then etcd, which is like a flat file database of the configuration of the Kubernetes cluster or the OpenShift cluster. And then we have the worker nodes, which is what you expect from the name. They are the one that run the actual workload, the application workload. So they contain a runtime environment, kubelet process to communicate with the Kubernetes master. And we can have a number of these worker nodes, and these number of worker nodes they are the ones that run the application pods or application containers. So from what does OpenShift offer? So OpenShift Container Platform includes everything you would expect in Kubernetes, but enhances it into an enterprise package. So the integrated and tested components of Kubernetes and delivered in a single package. So we have an enterprise operating system, which we'll talk about as one of the major changes in a bit. We have the container runtime, networking, we have the image registry, we have authentication, we have everything you'll see in a bit about what actually OpenShift contains. So if you think about Kubernetes, enterprise Kubernetes packaged together, basically what OpenShift Container Platform brings. There's a few flavors of OpenShift. We've got OpenShift Container Platform, where we deploy and operate the OpenShift in our premise or public cloud on our virtual or physical servers, but we manage it. We look after it. It's something that we will be running. There's a dedicated option where we have our own OpenShift cluster, but it's managed and operated by Red Hat and deployed in the public cloud. And then there's the online version, which is effectively hosted public cloud operation from Red Hat. Okay. If we look at it from an architecture point of view, then OpenShift is made up of pretty much what we saw in the Kubernetes environment. So we've got our master nodes. Now I've got their Red Hat Linux OS. That's obviously referring to an x86 cluster. Apologies. I'll discuss the differences in the operating systems in a little bit. We have that hosting the front end via APIs, so our developers and our operations staff can get in. So developers can come in and develop applications. Our operations staff can manage the cluster from an operations point of view. We have the physical layer underneath where we can deploy these VMs or servers on physical, virtual, private, public environments. The service layer that allows them all to communicate, and then we've got persistent storage, image registries where we would keep our images and where we provide storage should they require it to the containers, the pods. And at the top end we've got a routing layer that allows applications, external users to come in to the applications that we're hosting within our worker nodes. Okay, so very quick overview of what OCP is and what containers are and what Kubernetes are. So hopefully that was you sort of got an understanding of what that is. So when I crack on now with OpenShift Container Platform version 4 on IBM Power. So these are four main differences that I want to talk about today. So I want to talk about Core OS. So Red Hat Linux Core OS is a must now for master and worker nodes on Power. We have our Kubernetes operators. So these allow us to deploy, package, and manage the applications that we're running across our cluster. Think of it as an application management perspective, and I'll talk about that in a bit. The cluster upgrades are a simple interface, and this links in nicely to the Core OS aspect I'm going to talk about in a minute. And we'll see a video of the upgrades process, and then the installation process, the installation of the user provisioned infrastructure, and I'll briefly mention the installer provisioned infrastructure as well, and I'll take you through a video of that as well and how we can get the cluster installed in our environment. So let's talk about the first major change since version 3, when we were running everything on RHEL, Enterprise Linux. Red Hat Enterprise Linux Core OS, or just Core OS as we call it. They class it as the next generation because it's a single purpose operating system, and all it's there for is to operate as an operating system to manage containers. It's similarly based to RHEL in the fact that the software is RPM managed and the services are managed by system init, and so it looks very similar when you log on. However, it's immutable, or as they say here, controlled immutability. So we should not be changing anything on our Core OSs. Everything that we need to be done should be done by the cluster, should be done by OpenShift, and I'll show you a few examples of that in a minute. It also uses the CRIO container engine, and we saw the example earlier where I'm going to be using Podman. So that's just a daemonless alternative to Docker, and something that's been adopted quite rapidly across the industry. And I mentioned there we've got Podman as part of our COS. And one of the key things is that the updates are delivered as container images as part of the OCP upgrade process. So when we upgrade OpenShift, it actually upgrades the underlying Core OSs for us, hence why we should not have to do anything. These are well-tested OS images, and they're linked in, the dependencies are well linked into the actual containers and the operators that run our OpenShift. So we'll see in the demo how they all link in together, how an upgrade single click works together. And these updates are controlled by machine configuration operators, and so I'll mention the operators in a minute so you'll be able to understand how they work. If we compare the two, Red Hat has been around, Red Hat Enterprise Linux has been around for a long time, industry standard, high performance, suitable for lots and lots of different applications that we want to put on top of it. Core OS, self-managing, immutable, upgraded as part of OpenShift, tightly integrated with OpenShift, only really used for containers, and it means that us as infrastructure infrastructure administrators or deployers should not really have to worry about the underlying OpenShift operating system, shall we say, as we used to do with all the in version 3 when we were running it with RHEL 3.11 on Red Hat Enterprise Linux. Sorry. So as I said, it's tested and shipped with OpenShift, and I'm pretty certain you don't have to pay for CoreOS. It's part of the licensing with an OpenShift. It's managed by the cluster. It uses CRIO, it uses the clud config, and if we want to communicate to it, we can, as part of deployment, we can issue it an SSH key, and we can log onto it. And in fact, I think I do show you later on logging on and looking at the cluster, at the CoreOS operating system. Okay. So that leads me on to talking about machine config operators. What are operators? So this is core to how 4.x operates over 3.11. So we've had controllers. Controllers are a key part of Kubernetes. They run continuously across the master hosts. They compare the actual state and what is the intended state of an application, well, sorry, an object, so like a number of pods, nodes, services, routers, that sort of thing. And if they alter in their state, it tries to reconcile the state, so it brings them back into what this was. So, for example, if you had an application that needed 3 replicas of a pod, one of them died, it would try to start that third one up again. If you had an application or an image that said it had to use version 2 and you were running version 1.9, when you saved it as version 2, it would go away and find saved it as version 2, it would go away and find version 2 and upgrade it. Hence, like the same with persistent volumes and services. So we've had that around for a long time with inside the cluster. What we now have is with operators is application based. So conceptually, operators take the human operational knowledge that's encoded in the software and share that with customers. So operators, if we look at the top line there, we've got the application deployer, deploys the stateful application to cluster. Fine, everything works fine. Then a little while later, maybe they want to update or patch it or scale that application. The application services operation might be done by a different person, might be done by a different team. The original deploy might have left. What we're trying to do here is we're trying to bring it into a controllable state like we did with controllers. So they are a piece of software that eases the complexity of running that piece of software. They act as though they're an extension of the software vendors team. So the person who deployed or the team that deployed the software, they can put the configuration into Kubernetes, so the Kubernetes operator, to monitor the application. So that something happened to the application, should they need to upgrade it, should they need to failover, should they do to scale it, the code is written into that operator, and that operator knows exactly what to do. So Kubernetes itself knows what to do with that application. And we'll show you an example of some of these operators moving forward. And the key thing about version 4.3 is that the actual cluster configuration itself, OCP, is a bunch of operators. So operators operating on itself. So it knows what each individual element of the cluster, whether that's DNS, whether that's proxy, whether that's scheduler, is all part of an operator. So you can see what each one is doing and what each one needs to do to upgrade or to rebalance, for example. We write our own operators by using something called a custom resource definition. I'm not going to go too far into this today, but it's basically where we create a resource definition that allows us to define an object that Kubernetes knows about. We can then refer to that resource definition within custom resources, and then we can write the operator to look at those custom resources. So there are lots of examples out there, and I'll show you some in a minute, but this is one of the key elements moving forward within 4.3. We probably all know what Helm is. So Helm is the package manager technology for Kubernetes and OpenShift applications. We use a format called a Helm chart to define and install and upgrade an application. There is a tech preview in 4.3 around Helm that we can look at, but Helm is really good at the basic installation and maybe partly of seamless upgrades around our applications within the OpenShift cluster. The operator takes it way further. It takes it past day one package install. It takes it through, should do, a well-written operator through an upgrade process, through the full life cycle of application failure, backup and recovery, to the stage of metrics and logging, what we can do there, and obviously the scaling around and auto-tuning around it. So what we're doing is basically we're asking the vendors to provide the skill around how to run that application, package it up in an operator, and then Kubernetes will look after that operator. Within OpenShift Cluster Platform, OCP, it links to the Operator Hub. And here is a screenshot of Operator Hub. And we can see here a few different examples here. And I'll go on to Operator Hub in a minute to show you. And what I wanted to show you before I do that is this is a screenshot of connecting to my cluster. And I've done a get cluster operators. And we can see here all the operators that are currently running within my cluster. Now, these are controller clusters or platform clusters, as we call them. So these are the ones that are actually running OCP. So we're basically doing what we say application vendors should do. We're rolling everything up into operators so we know exactly what to do should one of these fail or one of these need upgrading. So let's quickly hop on to this. Hopefully this will work.
Before you do that, maybe just take a few of the questions that have come through, if that's okay.
Yep.
Okay, so there's a question: can worker nodes in OCP 4.3 for power run RHEL 7 or RHEL 8?
No. In Power, worker nodes have to be, all nodes in worker nodes and master nodes have to be Core OS.
Right, the next questions were already answered. Okay, so there's a question about whoever's running RHEL 7.6 can migrate applications to OS, the core OS, rather than migrating to RHEL 8. That's the question.
No, you can't upgrade a RHEL cluster on running, say, version 3 to a RHEL cluster running version 4. What you'd have to do is you'd have to make a backup of all your containers, your application level containers and pods, and then restore them onto the version 4 cluster that you build. It's not an upgrade process, if that's what the question is.
Okay, I think that's it for the time being.
Okay, no worries. So an operator hub, so within a cluster you'll see later, this is all the operator hubs you can see. We've got clip on database ones there. If we look at maybe an example like J, we can see a Eclipse J here. And the key I wanted to show you here was that the J is a good example because it installs multiple containers. It does PostgreSQL, a registry, key cloak, server, and multiple pods or cluster containers that want to communicate with each other. And I'll show you a screenshot of that at the moment. We've also got a few ones that we our own from IBM ones. So if we look at IBM, here for example is our operator for IBM block storage CSI driver. Fortunately, version 1.1, which is the one that's on Operator Hub, doesn't support Red Hat Core OS on Power yet, but the actual one that you download from GitHub does. So I will show you that I've installed that manually. And this is the process that I went through to actually install it manually, but obviously I installed version, the correct version that was suitable for my environment. So if I quickly log on to my cluster now, look at my projects. At the top, we should see a block project, which is where I installed it. So I do an OC project onto it. I do an OC get pods. We can see my controller running, and then I've got two nodes running, which would obviously be related to the fact that I've got two worker nodes within my cluster. Let me just show that. Yeah, so I've got two worker nodes, so I've got two nodes. So I've got my block controller running. My block controller is obviously monitoring my application being IBM block CSI node. And each one of those has got a number of containers running within each of them. Okay, so that's a bit blurred, I'm afraid. I'm not quite sure why that is. So this is an example of this is a screenshot of somebody who installed the Che operator on their x86 cluster. Now, the issue we've got is that most of the operators in Operator Hub are x86 Intel-based operators, both development, and they are addressing that. They are getting more power-based operators out there, so watch this space and we should be able to do it. But what I wanted to show you here was that this is our actual application in shade. This is the operator looking at it on the left-hand side, and you can see all the various Postgres and Keycloak containers and pods running off that single application. Okay, so installing OCP4. So if you look at that website at the bottom there, this is the Red Hat's OCP installation process. So we've got various different options on here. We've got AWS, Azure, Cloud, Red Hat, Bare Metal, Z, VMware, and bottom right corner you'll see Power. We've got Power on there now, which is excellent. So we've got two different modes of installing things. We've got installer provisioned infrastructure, and we've got user provisioned infrastructure. So installer provisioned infrastructure is what you'd expect it to do. It goes away and installs the actual hardware for you at the same time, and that's supported on AWS, Google Cloud, Azure, and Red Hat OpenStack platform, which I think is the one I'm showing you. So here we've got two options. We've got installer provisioned and we've got user provisioned. I like the way that they put a star on the recommended installer provisioned infrastructure. Yeah, that's but we don't have that option. If you click on the Power one, you get given this. You get given install OpenShift on Power with user provisioned infrastructure. So two steps. Each step has got multiple areas in it. So step one, as you can see in the top left-hand corner, what it wants you to do is download the installer. So download the installer is a binary, which basically is the OpenStack installer. You can download it and run it on a Mac, or you can run it on a Linux server. That's what the first part of it does. So we moved away from the old Ansible playbooks and we've now moved to the binary OpenShift installer. It wants you to pull down your secrets. So when you then run the install, it knows how to communicate with Red Hat, a key, so it can basically authenticate that it's allowed to pull down those images that are needed. It also wants you to download the command line interface. So this is how you saw me doing an OC earlier, how you can communicate with your cluster once it's up and running to be able to do some authentication around CSRs and what have you. And then the last thing is to pull down the core OS image itself. And on that link, you can trace that yourself. So points 1A and 1C are actually take you to the same site, which is this. At the top, we've got the client. So in other words, the OC and the kube control stuff for Linux, Mac, or Windows, so you can communicate with your cluster once it's built. And then the bottom is the actual real install, OpenShift install binary, which is in Linux or Mac format. So you have to download those first, or so the scripts I'll show you later actually do that installation for you should you want to do it automatically. You pull down your pull secret, which I've shown a couple of. I've blurred out most of it. I'm not quite sure I need to do that much blurring, but you can see that my pull secret has links to Key, Red Hat Registry, and CloudShift, OpenShift Cloud. Then it's the Red Hat Core OS image itself, and we have a number of different types of architecture and format in here. So we've got our bare metal version, we've got our OpenStack version at the bottom, obviously the one that I'm going to be showing you at the moment for PowerVM. So that is our QCOW2 image that we need to pull down. So when we pull down that image, if we want to use it in PowerVM, we need to convert it into a recognizable image that we can use. So we download and extract that image. We use the QEMU image convert command to convert it to a raw image. And then this is the process if we want to import it into PowerVC. So we attach the volume, a new volume, sorry, to an existing PowerVC VM. We do a DD to copy that raw image across to using block size 4 meg. To the new device. We detach that VM, so it's just a temporary LUN that we create to a VM that exists and then delete it. All we wanted to do was get the DD copy to that LUN. Within PowerVC, then we can import that image and we tell that it's a RHEL operating system and it's little endiness, and then we add the volume that we've just DD to as a boot set of yes. And there is an example of my image that I've now got in PowerVC, and that's the one we're going to use later to build our cluster. The second step basically points you to the OpenShift website on how to install a cluster on user provisioned IBM Power, there's two options. They can install it in a normal network with network connectivity, and we can install it in a network, a restricted network environment where we basically mirror the image catalog, image repository from key into our own infrastructure, and then when we do the build, we point to that mirror copy. But by default, it will want to point to the copying key on the internet. What do we need to be able to build our UPI cluster? So we need a bootstrap server. These are all running CoreOS, as I said. Now, bootstrap server is temporary. We only use it while we build the cluster. Once we build the cluster, we can get rid of it. But we need the control plane, or the master nodes, as we said. So we need 3 master nodes by default as a minimum in OCP version 4, and a number of compute nodes. So the number of compute nodes will depend completely on the amount of workload that you've got. So if you've got a large workload you want to run on it, maybe it's something related to a cloud pack, then you can size it as you wish, but the minimum should be 2, and the vCPUs and memory are as I've listed there. Obviously, the more compute nodes you've got, the more control planes you might need, but there's some good sizing documents out there on the internet about how you should size them. And again, it depends on your backend workload. The requirements for UPI. So we need access. So the top few I've already mentioned, I showed you in the previous slide, access to the OpenShift Cluster Manager. We download the binaries and the client binaries and pull secret. We need access to the internet to obtain a package during install, or we can use our mirrors repository. We need that CoreOS image somewhere available so our VMs can boot off it. When CoreOS boots, it uses ignition files, which I'll talk about in a bit. It doesn't use the cloud init configuration that we're used to with normal Power OpenStack based images. Mention how many we need, and then when it does the boot, it needs to be able to obtain an IP address either statically or from a DHCP server to establish connection to its ignition files, and I'll talk you through that process in a bit. Where we run the install from, we obviously need network connectivity, whether that's a Bastion server or a laptop. DNS needs to be updated with the node IPs and the cluster details. We need to provide a load balancer so we can control ingress to the applications, and if we want to do post-deployment problem determination of our environment, I recommend we put an SSH key in there. So what does this look like? Well, it looks a little bit like this for a production environment. So the mirror registry on the right hand side is obviously optional. We need a load balancer because obviously all the work that comes into the environment needs a load balancer, and a HTTP server to host the ignition file to be able to boot our master and our worker on our bootstrap our master on our worker nodes, some form of DHCP, DNS to be able to resolve all the internal DNS of the cluster, and potentially a Bastion host, but where we're going to run the actual installation from. What we can do then is we can condense this all into a single Bastion host. So a single Bastion host basically, and what we can do during the installation is create that Bastion host, or the configuration of that Bastion host, where we've got all those elements combined into one server. So for proof of concept, this is a lot easier, and this is one method I would recommend doing. You can obviously split individual elements of that off. If you say, well, actually, I've already got a DNS server, and this Bastion could point to that DNS server, but if you wanted to point it to a different, if you had a different proxy load balancing solution, and you want to use that for proof of concept or dev, you can break that off as well. While we prepare for the UPI installation, we need to run the OpenShift install. We need to unpack the OpenShift install. We need to make sure we've got the right version. We need to install the OpenShift client on our, this is the server that we're going to run the installation from, and we need to create the pull secret, which I've already discussed. But the actual installation is, this makes it look very simple. The actual installation really is just 3 steps. It's the preparation around these 3 steps that can cause the problems. We prepare what's called the install configuration file. So this is a YAML file, and I'll show you an example of that on the next slide. From this install configuration file, we create a manifest using the OpenShift install command. We tell it to build the manifest. These manifests are then injected into the ignition files on the next stage, and it creates the ignition files. The install is actually performed. So when we then boot our node, however we boot our node, our worker nodes, our master nodes, our bootstrap nodes, they actually go and look for these ignition files, and the actual installation starts automatically. There's nothing else after that we have to run other than just monitor the installation process. So I put a disclaimer in there, that a note in there that they do expire because the licenses certificates have 24 hours, so you have to regenerate them, but you can just empty the directory and recreate the ignition files. We provide an example of an install config file, and here we've got it's a YAML format, we've got cluster name, some proxy settings. We're not building the compute, so the worker nodes will be set to 0. However, the control plane, like the ETC, it needs to know how many of those to build. So we've got three master nodes, sorry, so it knows to build across 3 master nodes, or create the ETC across 3 master nodes. And then we have some information about our internal networking that we can change. And in the bottom right hand corner, this is where we put our pull secret that we mentioned and the SSH key that we mentioned earlier. And then we do the OpenShift install. So this is the binary we downloaded from Red Hat. We do a create manifests and we point it to our install configuration file directory. This goes away and creates the manifests. We then run the install create ignition configs, and that goes away and looks at the manifests and the install config file and builds the vital ignition files that we need. So when our VMs boot, they know what to look for, they know what to boot themselves. If we wanted to create these core VMs, how can we do this? So we could use OpenStack PowerVC, and we can use the images that we created previously. We could also use the ISO images, and I've got the steps in there. I won't take you through the exact steps. You can read through those, or we can use PXE boot. So this is just a way of booting the server, the VM, sorry, to point at the ignition files that we created. Okay. And I'm definitely not going to go through this, but I thought I'd leave this in there because this is what it does underneath. So as we start booting it, it goes away. The bootstrap server goes away and starts building a temporary Kubernetes control plane. The permanent control plane gets built from that control plane it built, and then the worker nodes get built from that control plane. So this is why it takes 45 minutes to an hour. It's going away and doing all this in the background. At the end of it, you're left with a working, hopefully, OpenShift cluster. Okay. Now, the process does sound a little bit complicated, but once you get your head around those core aspects, it's not too bad. However, one developer has written this very nice web page on breaking down all those steps for PowerVC, for PowerVM using PowerVC, and documented those in there. And he's told you about on the right hand side what you need, the introduction. It goes through each individual step. However, he's been even nicer, and he's actually created them into Terraform scripts. So he's created them into one Terraform that we can download from this website. And what it does, it downloads some Terraform files and some variable files, and then a directory called modules, which has subdirectories, which basically has all those steps in it, which we go through. Now, I'm going to run this for you in a little bit, but what I'd like to do is I broke those down and I went through each of those modules to see exactly what each step was doing to understand what the actual installation process is going. So it's a good way to look at it. And this is what it does. If we want to use that Terraform script, it builds the Bastion host for you using a RHEL 8 image on your PowerVC or your OpenStack environment. It installs a number of files, including the HTTP and the bind. It downloads the install binaries that we talked about earlier. It creates the install config, creates a manifest, creates ignition files for you. It places those in the HTTP directory on the Bastion. Then it gets the MAC address, where it previously got the MAC address, and sets up DHCP on the MAC address, and then it starts booting the bootstrap server. Then it boots the master servers, then it boots the host servers. And obviously during that process, the installation takes place. It then configures DNS and HA proxy on the Bastion node, downloads the client packages, does a bit of approval around the cluster, patches image registry, sets up a bit of NFS for us if we want it to, and reports the URL back to us during the build. So without further ado, let's run that demo.
Stu, can I interrupt you with some questions that have come up before you go to the demo, or would you prefer it after the demo?
I'm just conscious of time a little bit, Jyoti.
Okay.
Can we just kick this off for now?
Sure.
Okay, so this is that's not the install one. You get the install one up. This is the install one. Okay. So at the top, I've got my MacBook, my laptop, and this is the Terraform files that I spoke about earlier. And you can see under modules, in the bottom, I've got my PowerVC server. So what I'm going to do, I'm just going to show you an example of the Terraform file. And these are the modules I talked about. So all those individual steps like DNS and Bastion setup. And then I've got a parameters file. There you go. That's where it points to on the GitHub repository. So that's where I downloaded my GitHub Terraform files from. Sorry, my Terraform files from GitHub. Do you want to ask one of the questions now, then, Jyoti? While this is going through, I can.
Sure. Sure. So the first one I've got here is relating to future versions of Red Hat OpenShift Container Platform. If a new version, will it be available at the same time for Power 9 as it is for other platforms, x86, for example?
Yes, that's the plan. The plan is that they'll come into sync. They will be the same sync as the non-power releases as well. So that might take a couple of versions, but they will come into sync.
Mm-hmm.
Okay, so here I've just shown an example. What happened there? Where's it gone? Sorry. Of my variables file. So I've got a variables file that I blanked out some of the key stuff so you guys can't see my passwords. So I've pointed it to my OpenStack, my PowerVC, which is that one below. I've given it some information around public and private keys that I'm going to be using, my Red Hat subscription, and then more importantly here is the information about the Bastion node. So here I want Bastion node, I want 3 worker nodes, master nodes and 2 worker nodes. The template size I want to use, and then the image that I want to call. So you see that I've given it an image ID, and if I look on my PowerVC, you'll see that that relates to that image below. So 4.3, so it's going to try and build those. It's then got the install binaries I talked about and the client binaries I talked about. I've got my pull secret defined as a flat file, the cluster name. I've also told it to build some NFS, 300 gig NFS at the same time, and give it a cluster prefix of OCP v4.3. You'll see that I've got no OCP 43 instances running. So what I'll do is I'll kick that off and you guys can watch that running. If you want to ask another question, maybe, Jyoti, might be a good time.
Yes, so let me just find. Do you think there will be a move to multi-architecture operators like you can have with multi-architecture containers created with BuildX?
Yes, definitely. So hopefully the manifest will be clear that we can deploy a good question, a different architecture depending on, well, not depending on, but calling the same operator irrespective of which architecture we're running. Because most of those operators that we've got there, the underlying images are available on Intel and on Power, so like the MariaDB ones, for example. So it shouldn't be an issue to be able to offer them across multiple architectures manifests.
Thank you.
So I've taken large chunks of the timing out of this because you don't want to sit there and watch my screen for 7 minutes building a RHEL VM here on my Bastion. So it's gone and built my RHEL. It's now, you can see it's connected to it. It's now doing some provisioning to it. So the file information I said around, I think the first one was HTTP and bind utils installs. I can remember off the top of my head. It's still creating, so it's connecting to, I think it's connecting to, yeah, it's connecting to my Red Hat subscription there. And it's downloading repository information. Obviously, this is all within the Terraform scripts that have been provided. Maybe I should have cut some more of this out. I think we all know how repositories work. Okay, so now we're installing the binaries that I mentioned. Yeah, there we go, bind util, and probably a few prerequisites that it's going to need: HTTPS or flash through, Python. And, what's it doing now? Oh, okay, now it's going to get, there we go, the OpenShift install Linux file. So the actual binaries to install OpenShift, it's gone and grabbed those from the internet. Obviously, my Bastion has got direct connection to the internet. DHCP, I saw flash through there, it's configuring. And then what it should do next, it's building the manifest. So you see on the left-hand side, OCP manifest. So remember I said 3 steps. It creates the install file, builds the manifests, and then builds the ignition file. So now we've seen the ignition file being built on the left-hand side. And then it's updating ignition files with some of the information that we need specific to our cluster. And then it's now starting to build the worker nodes, the bootstrap nodes, and the master nodes. So they'll go off in the background and start these. So remember, as I said, once they boot, once they then find the ignition file, they start the configuration automatically. There's nothing else we have to run other than checking the fact the installation is in progress now, because we've done it all within our installation configuration files, our manifest files, and our ignition files. And it's going away and going to the setup at the back end. Are there any more questions, Jyoti, while that's running?
I think just one more. Could the Bastion node be created in an AIX 7.2 LPAR or RHEL 8 LPAR?
Sorry, the
Bastion node.
The Bastion server is because the Bastion server isn't part of the cluster, the Bastion server has to be a RHEL server. We don't support AX on the Bastion server, but the Bastion server is the one thing that does not have to be Core OS. The Bastion server is RHEL because it's not part of the cluster. You could get rid of the Bastion server at the end of it. You don't need to particularly use a Bastion server. It's that first chart I showed where it had the DNS, everything separately. If you've got those as an enterprise-wide infrastructure, you could just use those. You don't have to use the Bastion if you don't want to host all these separate levels of infrastructure requirements for the OCP cluster. Okay, so that's sorry, thank you. That's gone away now and actually built it. It's now saying it's waiting for the API to come. So if I log on to my Bastion host, the reason I'm logging on to my Bastion host because it's got the OCP client installed, and I'm going to go and connect to my cluster from the command line now. So it says, the log says, you've created a cluster. This is the user ID you can connect with, and this is the password you can connect with. Okay, so if I now log on, that's the IP address of my Bastion host. My Bastion isn't part of the cluster. It's just a way for me to communicate with my cluster. I seem to think I screwed this up in the video. Let me see if I cut it out. No, I didn't cut that. Okay. So that's the and we've got to remember as well, once this cluster is built, the bootstrap server isn't needed. The bootstrap server can be removed as well. It's just the worker nodes and the master nodes that we need. So these are the operators I was talking about earlier. So these are operators that make up the cluster. So these are all on the control node, all on the master node. So these are the main controls for that. And at the end of the installation, it comes back and tells you what host you need into, either DNS or into etc hosts and URLs. And at the bottom, you'll see the actual web console URL. So it says if you want to connect to this cluster, this is the URL that you need to go to. So I think I did this in a video too. So yeah, the Bootstrap node is used to just configure the OCP cluster. The Bootstrap node isn't needed moving on from post installation. I can't see the questions, but I can see the odd bit of text that flies through the top of the screen. So I think Richard's answering a few of them for me. Thank you, Richard.
Yes, yes, thank you.
I'll just go and gather the Password again, because I've forgotten it, because it's not very easy to remember. And there's our 4.3 OpenShift Container Platform front end. So as you'll notice, it looks an awful lot different from version 3. The dashboard is very good. The dashboard tells me what's going on as an overview. It tells me my pods are running, my nodes are running, storage classes. So I can see there, for example, all my masters and my worker nodes are ready. Okay, so the next one I want to show you is the upgrade process. Now, I'm always very dubious about buttons that say, click here to upgrade. I'm trying to find the edge of my screen here. It's because I've got underlined. So, but this is what I was talking about, though, the fact that we can upgrade from a single click on our OCP cluster, not upgrade, just upgrade the cluster, but upgrades the actual operating system underneath as well. So here we've got the cluster we've just built, so cluster 2. It tells me that it's on version 4.3.18, and I can just click on the update button should I require. But I'm just going to cluster settings first to show you. Let me move that cursor so you can see a bit better. And these are my cluster operators that I showed you from the command line. It shows that they're all on 4.3.18, which is what we'd expect. CO stands for cluster operator on the left-hand side there. If I query the nodes themselves, remember all these, query the cluster operators first, sorry, I forgot what I typed in there. We can see that they're all on 4.3.18, sorry, which relates to these numbers here. And here's my update button. As I said, always been very dubious in the past of an update button, but I've run it 3 times on various clusters in the last few weeks, and every single one of them has worked. If I look at the nodes in my cluster, all of them, remember, running Red Hat Core OS, 3 masters and 2 workers. If I look at the information around the nodes, I can query them using OC get and then the name of the node. It tells me information about them, so it tells me what architecture it's running, what its name is. What else is information down there? I've got the IP address, and well, it's a master node, so we shouldn't be scheduling workloads onto it. And down at the bottom, it tells some information about the actual node itself. So it tells information about the CRIO version it's using. Let me just tail the end of that so we can see that better. It tells us the kernel version, and it tells us the OS image that it's actually using as well. Okay, so now we select a new version. So on the cluster upgrade, it goes away. It's obviously talking to the image repository, the registry, and it's saying there's a version 4.3.2.8 available. So you simply click on the update button. And what this is going to do now is going to start pulling down all the images for all the controllers, sorry, all the operators around the cluster. So basically it can tell you what it's going to run. It's going to tell you what it's going to, it also will tell you what status is at and what version the operating system is going to be upgraded to. So here we go, it's downloading the updates as we speak. And what I'll just do for the interest of time for this, guys, obviously what I'll do is I'll just move it forward a bit. It shows us over here that we fast forward that we can see the events that's happening. It's downloading all the new images for the cluster. So remember, these are the platform cluster images that it's downloading, the ones that actually are running the cluster. In the bottom left hand corner, you can see the fact that the pods are restarting. Number of pods are restarting. And if I do get them now, what we can see, get cluster operators, we can see some have been upgraded to 4.3.2.8, some are still at 4.3.1.8. It's still running the process. It hasn't finished. And if we click on updating yet, we can see it's 81% complete. So what it does is it downloads the new images for the operators, and it restarts them with the new image. If it can't, it will roll back to the previous image. Once it's upgraded all the operators, it will upgrade the machine config. The machine config is the one that controls the OS of the underlying nodes. So the worker nodes and the master nodes will then get updated. So we can see there that it's pulling down various images. And these are where it pulls it from. It pulls them from the key repository. We can see the key repository there. I'm just going to fast forward this for the sake of time. And it's disabled scheduling on a couple of the nodes. So it does a master node and a worker node at once. So obviously it won't do them all at the same time because it wants to make sure that your cluster stays up. And there we say it's now said it's at 4.3.2. If we look at the cluster settings, they should all be, the cluster operators, sorry, they should all be at 4.3.2.8. They are, which is good. And then if we look at the nodes themselves, okay, just showing from the command line that the cluster operators are fine. We can see that the version on the nodes has been upgraded. So we didn't have the +4.5, what have you at the end. So they are now available. If we look at the master node again, just look at the end of it, we can see, hopefully, that we've actually got a new OS image. So the machine config has gone away and upgraded the underlying core OS for us. It's purged the pods from the nodes as it needs to, and it's upgraded them and then rebooted the OSs for us without us needing to do anything. So we got 4.3.8.1, and then we've got a newer version there of the core OS. So I was going to show you the cluster manager. So I'll just briefly show you the screen now. We can see all our clusters. So by the telemetry gets reported back to Red Hat. We can disable this should we require. We can turn this off. So what it does is it reports all your clusters back to you. And if we can see here that here's my cluster I just built and upgraded, it should tell me that I'm on, yeah, it's got correct number of master nodes, correct number of compute nodes. Any errors that it can see from the operators, and then an overview of all my clusters. So you'll see there I've got 4 listed. I don't know where that bottom was. I'm sure that's not mine. I'm sure somebody else must be using my ID to register with Red Hat Cluster. Okay, so that is installing and upgrading. So obviously the process has been trimmed down. It was an hour and a bit to install, an hour to upgrade. So that's where we were at. So what I want to do now for the last 25 minutes is to go through some of the actual work of my cluster. So this is my working cluster. So you can see at the bottom here, it's version 4.2.3. This is the dashboard, which is completely different from what you would know from the previous versions of OpenShift. Down here, we can see our pods, for example. We can see all the pods that are running in a certain project. So I can list all projects should I want to. All projects are there. We can do the compute as well. We can look at nodes. We can mark up a node as unschedulable if we wanted to. So in other words, if we wanted to do some work on a node, we can make it unschedulable. So the schedule would never send a workload to that physical server, that VM. If we look at pods, we can look at, so let's look at my own pods. I've got my own project to be a bit easier. Let's look at one of my pods here. We can look at the YAML for the pods, in other words, what it's actually doing. So all the background information about what I asked it to do when I built this pod. So a lot of information, a really nice GUI, to be fair. It works really well, and the dashboard tells me all that's going on across my cluster around usage and the nodes, the pod storage classes, etc. So a few things I wanted to show you before we finish today. You'll notice first thing here is that when it comes up is you're logged in as a temporary administrative user. So that kubeadmin user that it showed me at the end of installation is the one that I log in as. So if I go onto here, it says that you can add other identity providers. So here's a list of all the other ones that I could use: LDAP, HT password, and I've actually created a HT password one here on my my configuration. So if I go down to users here, user management, I can see my various users, and I can see that my configuration here is part of, I've got Cunliffe and I've got Spurway, and I can look at the configuration within there. Now, I do this by creating a secret for those. So if I just do my workloads and look at my secrets, sorry if I'm buzzing through this a little bit too quickly, but hopefully if you've got any questions, you can email me or ping me, or you can look at the replay. But I just wanted to show you my HT password authentication. So here is my HT pass authentication. It tells me the information around here, and these are my base 64 information around those. So if I wanted to edit the secret, I could edit the secret. I could add another user in here. So say, for example, I wanted to add a virtual user group user. I could give it, for now, I'll just give it the same key as my password so I know what I'm doing. I could save that, and I've got a new user within that group. So if I logged off, I've now got my cluster 1 HT password authentication, or the original one that I logged in as a cube password. So if I go in as this user, and what did I call that? I called it VUG user, I think. And it should be the same password as my previous password. Did I call it VUG user?
Yeah, I think you did.
Okay, just me, just not typing correctly. So you'll see now that I'm logged in as VUG user, but I've got a lot less information around the left-hand side. I haven't got any information about the nodes or the cluster-wide administration that I had access to now. But what I can do is I can create my own project. So if I go to EVU demo, I've got my own project now that I can work on. So you can give a user access to their own project. You can give them control over what they do within that project. So just for the rest of this demo, I'm going to log out and log back in as Cube admin user, just to speed things up a little bit. So here we go, I've got access now. If I look on projects now, what you'll see, probably down the bottom, because alphabetically, is the VUG demo one I created, and the fact it's assigned to that user that I created as well. So what I'm going to show you, so let's look at, there's a new window here. So we've been under administrator all this time. If I go into developer now, we can see, I'm going to go to my project. Sorry, I should have done that before. So my project, it shows me my applications that I've got available. So these are the ones that I built, these ones that I'm running as my user in Stu's UK project. So let's say I wanted to do a new deploy. So I click on add here, and I've got a few different options. I've got from Git, an image itself, from a catalog, Docker file, YAML, or database. So I'm going to show you a few examples of these today. So the first one I'm going to show you is a simple YAML file. It comes up with a blank YAML file. Let me just get an example of one I wanted to use. So let's see, let's look at this rel 7 YAML file here. Ooh. I'm going to just cut and paste that YAML file, and I'm going to place it into the configuration here. So this is going to tell me I'm going to build a pod. I'm going to give it a method name of rel 7 test. I'm going to put it in my project. The container is going to be one container called rel 7 web. I'm going to pull that image from Red Hat registry, and I'm going to run the command sleep for 10,000. And I've got a secret to be able to communicate with registry Red Hat IO. So it should do. I was going to video this one as well, but I thought, no, I'll risk it. A live demo is always worth running. There we go. So it's pulled it, it's created it. We should see that it's running fine. Sorry. And then we can see there that I've got access to that pod. Now I call this as a pod. So you'll actually see that it's not listed as my applications because it's an individual pod that I call from a YAML file. If I go into my pods, and excuse me, this is probably not the best way to get to them, but I'm going to go to all the pods that I'm now running. You'll see here's the one I just created. And the fact that I didn't create it as a deployment configuration, it's classed as no owner. So if I killed it, it's not going to come back. So let's show you that. Delete pod, terminating, and eventually that will go and it won't recycle like it would if I was going to do one of the others. One of the other options is deploying from a Docker file. So as I mentioned at the beginning of this presentation, we have the option to build something from a Docker file. So if I go to GitHub, where's my GitHub entry? Here's my GitHub entry. Let's look at my repositories. I've got one called Lab Services website. It's very simple. It's got a Docker file here. The Docker file brings down an image. It installs Apache. It copies a website directory over. It copies the HTTP directory, changes a few permissions. It exposes port 8080, and then it runs HTTP for me. That's all it does. There's my configuration file, and there's my website directory with all the other options in there. So, oops, where's that gone? Sorry, I clicked back too far on that one. So what I can do, I can place that GitHub entry where my Docker file is into my build. Put it in there, click on validate, goes away. It's going to tell me some information about it. It's giving it an application name that I want to run. So tell you what, I'm actually going to run this in your I'm going to run it in the project I just created. Let's test that project I just created. Apologies for that. So I'm going to put it in that one. Yep, it validates it. It's going to call it Lab Services Website App. It's going to name it defaults to. I'm going to deploy this as the deployment configuration. And I'm going to create a route so we can get into it. Click on create, and if the permissions are correct, what I should see is it building now. So it's going away and it's looking at that Docker file and it's running through the steps in that Docker file. If I look at CVC, it's build number 1 is running and it's got a build configuration. It's also created a service. So in other words, it's linking point 80 to pod 80, so it knows where the pod's going to be. And then it's created me a front end route as well. So these are the resources that are available. And you'll see the different colors appearing on this different side here. Now the build is complete, it starts creating a container from that build. And there we go, it's now created that container and it's running. So in theory, if that's worked and it's gone and done the installation as I expected, if I click on this, yeah, there you go, look at that. Beautiful UK Systems Lab Services website. As you can tell, I'm not a HTML programmer, but there you go. So that's gone and done that build. We can see an overview here now of what it's got. So it's got 1 pod. I could scale that up to 3 pods. So what's going to happen is it's going to create 3 copies. Obviously, this is a stateless application, effectively. It's gone and created 3 pods. If I click on resources again now, that we've got now 3 pods, effectively we're running the same image, the same application from the back end. We could go and edit those if we wanted to. I could edit the configuration. I can say just have 2 and it'll go away and run 2. In fact, I'll do that for you now. So if we edit deployment configuration, I go down here. This is another way of doing it. So I've got replicas, it changed it to 3, change that to 2 and save. So this is where the controller kicks in. So the controller recognizes, just a minute, your configuration says that you want 2, but you've got 3. So you can see here it's terminating one of the pods, which is exactly what I wanted to do. Now, imagine that the developer here has changed this code and we want to rebuild it. So we've got a little icon here. We could go to there, or we could go to the tab that I was using earlier. So if I click on, oh, sorry, wrong tab. If I click on source GitHub here, so edit the source code, my developer has said to me, I've got a tag, a version 1.1 that I want you to deploy. Okay, he's told me that. So we can come back into here and we can edit the configuration again. So where we edited it earlier, we just go down here and we find where it was calling the version from. Oh, sorry, I'm in the wrong place there. It's not the configuration, it's the build configuration, my bad. So within the build configuration, I can edit the build configuration and I can say, I'm going to say I want you to reference version 1.1. So while we do a build, the build will go in the background and the pods are happily working away, no problem there, they'll carry on running. And as soon as the build gets completed, it will say obviously that the pods need to be reinitiated, so the pods need to point to the new build image that I've just created. So hopefully I changed that in the right place, and we'll see the build complete, and then we'll see the pods rebuilding. So there we go, it's creating a container. If I put it on this view, you can see it a little bit better in the fact that it's starting the first one. As it starts the first one, it stops the first one on the original, starts the second one, and then stops the second original one. So we'll see there's two pods, but these two new pods have meant that are running perfectly, so it means that the old two pods can be closed. So then in theory, if I refresh my website, we now see that the only change he made was the title is now blue and bigger. So it's not exactly a massive change, but you get the idea. It's whatever the application is, what the application wants to do. So the last thing I want to talk you through is storage. So we've had some changes in storage recently. So our shared storage at the moment solution is NFS, and we've got Spectrum Scale hopefully coming out soon, and Ceph further on down the line. But we do have block storage using the IBM block storage CSI driver that I showed you earlier. So let's have a quick look at the storage. So if we go back into the administrator tab and we go down to storage, sorry, the screen's freezing. We've got my storage classes. So here I've got a Power VC CSI volume storage driver. I've got my NFS storage, and I've got two block storages to do different V7000s that I've got here. So if I wanted to create a persistent volume and a claim against that persistent volume, I could choose, for example, my NFS storage, claim name, let's call this VUG PVC1. It's a shared access because it's NFS, and I'm going to give it a size of 3 GB. If I go back to my persistent volumes now, we can see it's created and it's been able to bond it. So in other words, that claim has claimed that physical volume. If I go back now to my application that I was running, what I can do is I can attach that storage that I've just built. So I can use an existing claim. So hopefully if I pull that down, I can see my claim. There we go. Give it a mount path. Or let's call this just NFS for simplicity, and save that. And again, once again, oh, I've gone back to my screen, sorry there. Once again, you saw the fact that the configuration has changed. So the deployment configuration says, oh, this wants a physical volume claim against it. We've not got one, so we have to restart the pods to that new configuration. And there's my two new pods being created. So let me just have a look at the new pod. And we've got our NFS file system there, team directory NFS. Shouldn't be anything. Ooh. Let's say touch or echo shared to NFS.file. Okay, let's go on to our other pod. Which one was that? Was that one? There we go. Another one, if we cd to NFS, cd to NFS, we can see the NFS.file there that we created, show the read, write, shared, execute. Okay, so that's a simple NFS shared. Obviously, the file side of Spectrum Scale will be along hopefully very, very soon. If I look at block, I'm actually going to do block on my other server, because what I've got on here is I've got if I look at my topology, I've got a MariaDB instance that I created earlier. Now you notice previously I created the persistent volume claim outside. I created it in the admin window, and then I added it to my my configuration, my default configuration, my deployment configuration. What I can do, I can also do when I do the add storage, I could create a new claim at the same time. So then let's say I want to create some of my block storage and I want to call this one /data. It's single, oh, sorry, name. So this is, sorry, not VUG, VUC1. I want to create it, let's just create it at 1 gig now. And the mount path, sorry, let's put data into mount path. So if it hasn't timed out in the time I've been doing this, let me see if this is on my SVC, my B7000, which is that one that it links to when it's doing the claim. It's scaling the pod. Again. Oh, okay, maybe the name's different. Let me just find it. Let me just see if it's mounted it first. Come on, button. Yeah, so it's mounted. I don't know why my V7000 hasn't refreshed itself. So if I go into data, for example, there won't be anything in there. But if I do a df -h dot, you'll see that that's my 1 gig server that I created from my multipath, which is now being mapped to it. Oh, there we go. It's come back online now. So there's the volume that it just created, the block run. If I do a view mapped hosts, it should tell me that it's mapped to one of my worker nodes. Yep, it's mapped it to all my worker nodes. So my underlying container can see it. And we saw my container there, being able to see it. If we do a echo data to, I don't know, data.file, and we've got the data.file there now. Now, if I wanted to remove that, I could remove that persistent claim, I could remove that volume, I could basically say, no, I don't want to use that volume. I could edit it manually, for example. So I'm trying to show you as many different places here where we could do that. But if we look under the YAML configuration now, and I go down to specific volumes, we can see here we've got my volume claim that's pointing to that particular PVC. Let's get rid of that, and there should be somewhere a mount point as well. Yeah, there's the mount point for my volume, and save that. Okay, what you'll see is that it doesn't actually, because obviously it's got to terminate and return and rebuild the pod without that mount point. So hopefully, if this has worked, if I do a df, yeah, /data is now gone, but it's still there. That persistent volume is still there. If I look under my persistent volume claims here, my persistent volume claim is still there. So there we go. There's my persistent volume claim. If I look on my environment here, my V7000, it's still there. So what I can do, I could add that to another. So if I built another environment, I could build that. So let's again do this from a YAML file. So I'll show you a certain YAML file. If I go back onto my cluster here, have a quick look. I created a YAML file previously, so rel with storage. And did I create it? VUG demo PVC2. Let me just check that's the right name before I go any further, because I don't want it to. VUG demo PVC2. Yeah, okay. So what I can do is I can now apply this YAML file into a new configuration. So I can add an environment from YAML, paste that file, and if I haven't had any typos, what we should do is we should go and see it pulling down the rel 7 image again, which is actually already in our local inventory, so it shouldn't need to pull down, but it will create the container. And hopefully, again, so I've not made any mistakes in the syntax. I have created this in the syntax. Okay, apologies. I don't know where I've done there. Oh, I might have already done it actually. That might just be a DM issue. Let me just check. It might have worked. Yeah, so there is data. So there is the same repository. I called it data, I didn't have to. If I look at that file, there is the file I created when it was on the MariaDB LPAR. Okay, and if I wanted to delete that, I could delete pod. And because I didn't delete it, the persistent volume claim, the persistent volume claim is still there. We can still see it over here, so it's still available. However, if I wanted to delete it, I could delete the persistent volume claim and the underlying physical volume. And as long as nobody's using it, obviously this would fail if while that RHEL 7 pod was still up, but it's obviously I'd taken it down previously, so it's gone. And then if I refresh that, as I said, it's taken a little bit of time to refresh my SVC window, but we'll see that that will eventually go as well. So sorry if I've rushed through a little bit as well, but as always, I always think I've got more time than I have. Just a quick summary, 4.3 and 4.4, to be fair, now is supported on Power, not a chance to upgrade to 4.4. It's supported on 9, but I'm running it on Power 8 in my lab. If you've got 6 free cores, then you can set up a proof of concept across your Power environment, and a number of links there. The top one is a link to the Montpellier Centre, so the Montpellier Client Centre. I've got some very good examples. They've got OCP 4.3 running on Power there. They can demo it for you. There's a Redbook available. There's an OpenShift Try site. And then the links that I've referred to throughout the session are below. Okay, so that's it from me. Thank you guys for attending. If you've got any questions, please give me a shout, and I will try and support you. Obviously, if web services can assist you, please contact me for help. Thank you.
Thank you very much, Stu. Gosh, you went through a lot there. And
Yes.
Almost at the end, there was an ice cream van that went past, a very musical one, and I was going to get you one and send it over, but he's gone now, so sorry about that.
No problem.
Thank you so much. There are a few questions, so we'll just take those before I stop the recording. Just trying to see where we got to. Right, there was a question about the Bootstrap VM, but you already answered that. It can be deleted once the installation is complete. The upgrade of the CoreOS 4.3.18 to 4.3.28, it didn't ask you for a reboot of the VMs at the end, i.e. reactivation of LPARs?
No, it does that for you. It's part of the process. So once it's evicted the node, we restarts the kernel on that node.
Okay, thank you. Is external networking typically routed out of the worker nodes running the pods, or does it physically go through the master nodes?
Good question. So the routing on the routing can go via directly from the worker nodes should they require external access. Yeah, so it's we can use a proxy on the worker nodes, on the master nodes, or we can do direct connectivity from the worker nodes to the internet.
Okay, thank you. I think this is it at the moment. Let me, just checking. Okay, so there's another question. This is a proof of concept implementation of OpenShift Container Platform on UPI deployed on the same network. Is there any information you can provide on the subnets and floating IPs to be created in OpenStack for a production implementation?
Not sure I fully understand the question. Maybe can the person who asked that just email it to me? Maybe that'd be easier, and I can read it from there.
Okay.
Yeah, if you can just give a bit more detail about what it is you mean from a subnet perspective from OpenStack, and then I'll try and answer that for you. Thank you.
And there was a question about if we can install IBM Cloud Packs on OCP 4.3, and the answer is yes, those supported on Power. Somebody already answered that. How to configure, sorry.
There's only two which are actually supported at the moment on 4.3 on Power, application and data. So the other ones will be coming along throughout the year.
How to configure the OCP to increase pods automatically when overload is detected in CPU, RAM, network, that kind of thing?
Yeah, that's a good question. I've actually investigated that, to be honest, especially with the user provisioned infrastructure. I'm not sure how easy that will be. I guess we can. I know that I've seen people installing additional worker nodes via Ansible as well. So I'll try and get some information about that and post it out by yourself or Josie or on Twitter, because it's something I did need to look at, but I've not looked at how we expand the worker nodes automatically anyway.
Okay, and that's a good point. As you can see, Stuart's Twitter handle is displayed on the screen now at STU Cunliffe. So yeah, and mine is on most of my communications, so at Jyoti Dodia. Does OCP 4.3 have policy rules to automate the number of pods based on resource usage, i.e. auto scale of pods? It's sort of similar question.
So there are policies that we can place on nodes to be able to determine the usage and how busy they should be, and whether they should evacuate pods to other nodes should they get too busy, should they be disk starved, memory starved, or CPU starved. Obviously, at the moment, Red Hat, so CoreOS isn't supported on RMC, so we can't automatically scale a VM should we need to. But I think that's in the pipeline as well. Don't hold me to that, but I did see some communication about dynamically LPARing CoreOS to be able to grow the actual size of a node as well, should we need. But yeah, there's policy-based actions can be done against certain nodes and workloads projects.
Hey, thank you so much, Stu. We can stay on a couple more minutes, and apologies for overrunning slightly. Thank you everyone for joining. Today, the next session for PowerVog, I'm still organizing, and once that's finalized, I will post information in the usual manner on the PowerVog info page, as well as via emails if you've subscribed to the PowerVog series. So watch out for that. There isn't a next session, a next date as yet at the moment, but there will be. I'm working on it. Let me stop the recording for now.